Hi, welcome to the video lecture on the chi-square test for independence. Chi-square is actually written with this Greek letter that looks like an X. It's usually spelled C-H-I, but it's pronounced chi, so it's chi-square test for independence. We'll start with an example. This is an example. I made up the data, but the scenario is one that I've actually been working with someone in the music therapy department, helping them analyze some data that they've collected, and this is the scenario. So one of the things they looked at was whether there's a relationship between the amount of voice disorder somebody has, none, moderate, or severe, and what their main instrument is that they use in their music therapy, whether they do singing or whether they use some sort of instrument. And so suppose we collected this data. This is a cross-tabulation that you'll recognize. You recognize cross-tab from earlier on in the course. But just to be clear, the cells here represent frequencies. So the 39, for example, means that there were 39 music therapists who sing as their primary instrument who don't have a voice disorder. 21 who have no disorder and are use an instrument. Okay, so etc. That's what that means. So the chi-square test for independence allows us to test whether two categorical variables like these two are related. And in this example, the two variables are what the instrument was, whether it's voice or something else, and the category of vocal health, none, moderate, or severe. So in the previous hypothesis tests we've done, we had three different possible sets of alternative hypotheses. We had the not equal to, the two-tailed option, and then the less than and the greater than. In this one, there's really just one set of hypotheses. And the null hypothesis is always that the variables are independent, which is another way of saying they are not related, versus the alternative hypothesis is that they are dependent or related. Okay, so basically we want to assume that there is no relationship between the two variables unless we can show the alternative hypothesis that there is a relationship. All right, so for this example, we would say that the primary instrument and the level of vocal health are independent of each other. That would be the null hypothesis, and the alternative hypothesis would be that they are related in some way. Okay. All right, so let's go over to StatCrunch. I've typed this data in already. No disorder, moderate, severe, and StatCrunch requires that you type in the labels here into a column. So our data is right here. So to run the test, we're going to go to Stat, Tables, Contingency. Here we have the summary. So we'll click the summary. Our three columns are no disorder, moderate, and severe. So I'm just going to hit Shift and select all three of these categories. Our row labels are in variable 1. That's where we have our two row labels. And we're going to pick the chi-square test for independence. Click Compute, and it tells us what our contingency table was, what our totals are, and this is the chi-square test. So this value here is our test statistic, and this p-value is of course the p-value. Okay, so copy and paste that over into your homework, and I've done that here. So if alpha is 0.05, then we would need to state reject H0 if p-value is less than 0.05, and our conclusion then would be reject H0. There is sufficient evidence to conclude that these two variables are related. Okay, and I'll change this. These two variables are related to each other. All right, so Based on this data, we can conclude that there is a relationship between the primary instrument and the level of vocal health. So that's all you really need to be able to do to conduct the test. We'll get to the effect size in a minute. But I can't not tell you what's going on behind the scenes here. This data here is called your observed data. What happens with every hypothesis test, or with every chi-square test, is that there's what they call expected data. So we could do some calculations and it would tell us what values we would expect to get for these frequencies if these two variables are truly unrelated. And the chi-square test compares the observed and the expected. If they're far apart, then that gives you a large value for chi-square and a small p-value. So anytime you see observed and expected, observed is the data you collected, expected is the data you would expect to get if the null hypothesis is true. Let's just do another example here. This one is whether there's a second conviction for drunk driving based on the treatment or the penalty that was given for the first conviction. So we've got this data here, and I've got it plugged into StatCrunch. And we can just go to Stat, Tables, Contingency, here again with Summary. Select our columns. We've got second conviction and no second conviction. For this one, our row labels are in the 6th column. And let's look at the expected count as well, just so we can take a look. And we want to run the chi-square test for independence. All right, so here our test statistic is 0.4167. Our p-value is 0.8119. So if we're using 0.1 as our alpha, we would fail to reject H0 and say that there is not sufficient evidence to conclude that these two variables, the recidivism and the type of sentence received on the first conviction, are related. And I want to point out here that saying we cannot conclude that the variables are related is different from saying we can conclude that they are not related. Okay, so that's a somewhat subtle difference, but it is a difference. And just so we can see, this tells us what the expected values are. So this tells us that there were 52 people who had a second conviction who got a jail sentence for their first one. If the variables were truly unrelated, we would expect to get about 54 in that cell. Here we would expect to get about 32 in this cell. And you can kind of tell from looking at these that the observed and the expected are pretty close together. So that did not give us very strong evidence for the alternative hypothesis, as you can see from this value, the p-value. All right, so let's talk now about effect size. So the measure of effect size is, again, from Cohen. This one's called phi, another Greek letter, and it's calculated as the square root of the chi-square test statistic divided by the sample size times k minus 1, where k is whichever is smaller between the number of rows or the number of columns. So here the guidelines are 0.1, 0.3, and 0.5 for small, medium, and large. So let's do an example. So if we look at our first example, the musicians, there were 208 total observations. And you could get that by looking at the output from StatCrunch that shows up on the output. It tells you, so it tells you in the output what the total values are. Or you can just add up the cells. So there were 208 observations. The test statistic was 7.6546. So the test statistic goes in the numerator. The sample size goes in the denominator. The table had 2 rows and 3 columns. So we picked the smaller one of those 2. So 2 minus 1 down here is just 1. So we do 7.6546 divided by 208. And then take the square root. When you do that, you get 0.1918, which is right between 0.1 and 0.3, the guidelines for small and moderate. So we'll call that small to moderate. In the second example, the recidivism, there were 353 total observations, so n goes in the denominator there for 353. The test statistic was 0.4167, so that's in the numerator. The contingency table was 3 rows by 2 columns, so k is 2 again. So 2 minus 1 is just 1, so we do 0.4167 divided by 353, and then take the square root, and we get a very small effect there. Now, to do this in SPSS, I'm going to pull up SPSS and show you how to do this. I've got an example here that has textbook prices in it, and the 2 variables we're going to look at is the textbook subject. We've got textbooks that are biology, chemistry, physics, and medical textbooks. And we've got 2 different kinds of binding. We've got paperback and hardback. And what we want to know in this example is, are the 2 variables related? Is there a relationship between the subject of a textbook and what kind of binding it has? So to do that, we'll go to Analyze, Descriptive Statistics, just like we did before when we did crosstabs. So it's under crosstabs. And we'll take one of the variables, move it to row. We'll take one variable and move it to column. And it doesn't matter which one's which. You get the same value either way. Under Statistics, put a check next to chi-square. Click Continue. And then, under cells, if you want to see what the expected cells are, you can do that so you can compare. We won't do that for now, though. So just click OK. And this gives us 3 things we need. It gives us the case processing summary, gives us the sample size, which we're going to need for the to do the effect size. It gives us the observed frequencies, and then it gives us the results of the test. This for the chi-square row here, the value is the chi-square test statistic. So 0.649 is the chi-square test statistic. And the p-value is asymptotic significance. It's 0.885. Okay, so I've got those things labeled in here, so you can go back and look. So based on that test, based on that output, we'd set up the hypotheses that the subject and the binding are unrelated for the null hypothesis versus related for the alternative hypothesis. We get our test statistic and p-value from here, from the output. Reject H0 if p-value is less than 0.05. We'll assume 0.05 unless told otherwise. And based on that, we would fail to reject H0 and say that there is not sufficient evidence to conclude that these 2 variables are related. For the effect size, I'm going to take the square root of the test statistic, 0.649, divided by the sample size, in this case was 55. The contingency table here had 2 rows and 4 columns. So the smallest of those is 2, so we still have 2 minus 1 in the denominator. So we do that calculation and we get 0.1086, which is a small effect size. All right, so that's it for this lesson then. And as always, let me know if you have any